All right, hello everyone. We are back for the last part of chapter 9. So let's talk a little bit about it. So we spent some time talking about, the true nature of electrons. We talked about orbital diagrams, talked about electron configurations. And so today we're going to talk a little bit about why it actually matters and that unlimited power of the quantum mechanical model and how much it predicts about the behavior of the atoms on the periodic table. So this is kind of what I just said, but let's make sure we take some time to review. So we talked about electronic nature and how the electrons lie in that electron cloud. So orbitals are probability maps that tell us how likely we are to find an electron in a certain location. And electrons occupy these orbitals in pairs of two, if possible. Remember, spin up, spin down. And they fill the orbitals from the lowest energy up to the highest energy. But why the heck do we care about any of this? We're going to spend some time today talking about how this influences the chemistry these atoms can participate in. So let's talk a little bit more in detail about that electron cloud. So we've spent some time talking about how electrons lie in these orbitals in the electron cloud, but not all electrons are truly equal. So remember, all electrons are kind of like held onto the atom because they're negatively charged, and that nucleus is positively charged. So that positive-negative attraction holds the electrons onto the atom. But electrons are also negatively charged, and if they're around other electrons, they're going to repel each other apart. You're not going to be able to bring them fully together. They try to stay as spread out as they can, and that's kind of what the orbitals are telling us. So it means that, there are electrons that are closer to the nucleus and electrons that are further away from the nucleus then. So you can kind of see that here, right? So I have a picture of Bohr's model of the atom just because it's a little bit easier to look at, but you can kind of translate this in your brain to that quantum mechanical model in thinking about the energy of those orbitals, even though I'm kind of showing you orbits, okay? So you see that we've got kind of a ring here. We have two electrons that are closer, and out here we have a few electrons that are further away. So what does this mean? What the heck am I talking about? Well, we can kind of start to separate out these electrons into two groups, and that helps us determine how they can actually participate in chemistry. So, the outermost shell of electrons, those very ones on the edge, are called valence electrons. So valence electrons. So they are the furthest group from the nucleus. And because they're so far from the nucleus and they have other electrons like kind of below them in energy that are closer to that nucleus, they have a little bit more freedom to move around and connect with other atoms. We call it shielding. So the inner electrons shield the valence electrons on the outside from feeling the full pull of the nucleus. They're repelling the electrons that are in those lower energy orbitals and each other. So they're all around the outside and they don't feel as strong of a pull to that nucleus as those innermost electrons do. And we call those innermost electrons the core electrons. So now we have the core electrons and we have the valence electron, core and valence. So core electrons are the innermost electrons that lie closest to the center of the nucleus of the atom. And so those core electrons here would be like these two with the yellow circle, and those valence electrons would be out and around the edge, that outer circle here. So again, those core electrons like kind of do what we call shielding, and they shield the valence electrons from feeling the full force of that positive attraction from the nucleus. So valence electrons are the only electrons that participate in chemical bonding. All of those core electrons are not going to be able to participate in forming a chemical bond or forming ions or any of the other things we've talked about, okay? So those core electrons shield those valence electrons, and that allows them to participate in bonding. So the core electrons have less freedom to do this because they're kind of being shielded from the outside by those valence electrons. The valence electrons are going to go before those core electrons do. And it's actually really, really hard to remove a core electron from the atom. So, how do we identify core and valence electrons when we are talking about a electron configuration, for example? So again, remember those core electrons are close to the nucleus and the valence electrons are the outermost electrons. And so valence electrons are all the electrons with the highest principal quantum number. Valence electrons are determined by the principal quantum number. Not necessarily the ones with the highest energy, but by that principal quantum number. And the core electrons are everything else. If it's not valence, it's core, okay? So we've got two different images on here on your screen when we're talking about core and valence electrons. So silicon here, this is the electron configuration for silicon. So this says it's 1s2, 2s2, 2p6, 3s2, 3p2. So those core electrons are going to be the 1s2, 2s2, 2p6, and we know that those are the core electrons because they do not have the highest principal quantum number. The highest principal quantum number we see here is 3. So this is going to be 3 valence electron, the outermost shell, therefore, is 3. So any orbital that has that principal quantum number of 3 is going to be a valence electron. So the 3s2 electrons and the 3p2 electrons are going to be valence. Everything else is core. And we say the same thing down here with selenium. Okay, so this makes the point about the fact that it's not the highest energy, it's the principal quantum number that determines this. So in the electron configuration for silicon that you see, selenium that you see here, you can see that we kind of have that weirdness with the 3d10, right? 4s2, 3d10, 4p6, right? 4s2 and 4p4 have that highest principal quantum number of 4. So they are the valence electrons. Everything else highlighted here in blue are the core electrons. So it doesn't matter that that 3d10 orbital has a little bit higher of an energy than that 4s2. We are not going by energy. We are going by principal quantum number only, okay? So that principal quantum number tells us which electrons are valence and which electrons are core. Let's do some examples, okay? So we're going to do one example with a orbital diagram and one example with an electron configuration when we're determining what the valence electrons are. So first up, bromine. That is our bro there on the screen, bromine. I've been waiting all semester to make that joke. So we're going to do bromine. Bromine here is this orbital diagram that I've drawn. So if I want to look at this, I need to identify which ones are core, which ones are valence. Well, remember, it's the principal quantum number. So the valence electrons are 4s2, 4p5. So they have that principal quantum number of 4, so they are the valence electrons. And everything else is core electrons. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Those are the core electrons, which you can see written out here. And so that makes, so we have 7 valence electrons, which makes sense. 1, 2, 3, 4, 5, 6, 7. So if I asked you how many valence electrons there were, you could tell me there were 7 valence electrons. So let's do the same thing, but let's do it with an electron configuration. So if I told you that this on your screen was what you see is the electron configuration for krypton, the electron configuration for krypton, let's figure out which ones are core and which ones are valence. So I'm going to scan through this here, and I'm going to look for that highest principal quantum number, which in this case is, again, 4. So then that tells me that the 4s2 and the 4p6 are going to be my valence electrons. 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10 are going to be our core electrons. And so if I asked you how many valence electrons there were, you could tell me that there were 8. 4s2 and 4p6, 8 total electrons, 8 valence electrons. So it's important that you can identify which ones are core and which ones are valence from the orbital diagram or the electron configuration, because we use that information to determine things about the kind of bonding as well as some other trends on the periodic table. So remember, the valence electrons are the ones that participate in chemical bonding. They're that highest principal quantum number, that outermost shell, and then everything else is in the core. So I gave you some other ways to practice here. You could either write the orbital diagram or write the electron configuration, and then you can determine which ones are core and which ones are valence. So go ahead, go back, do some practice for yourself on your own without me guiding you. So like I mentioned before, why in the world, Professor Thomas, do you keep telling me all this information? Why does it matter? Again, because that number of valence electrons and how they're positioned in these orbitals tells us about the kind of chemical reactions, the kind of chemistry they can do. And each column on the periodic table actually has the same number of valence electrons, and that's why their chemistry tends to be similar. Remember, we talked about how the alkali metals are like so reactive with water. If you watched my YouTube video, you would know, but they are super stinking reactive with water, and they're all super reactive with water based upon the fact that they all have just one valence electron, and that one valence electron influences that chemistry they have. So when Mendeleev was arranging that periodic table, he thought he was going to do it by atomic mass. That led us to arranging everything by the number of protons, but when we did that, we were actually secretly arranging it by that number of electrons in these orbitals and how these electrons fill those orbitals, okay? And so what that tells us is about things like the size of the atom, something we're going to talk about in a second called ionization energy, and how much like a metal something acts like. So information like this contained in the periodic table was actually what allowed scientists to seek out and discover those missing elements. So like, again, when Mendeleev was arranging that periodic table, he basically set everybody out on a hunt. Everybody was going to get, like, discover an element on the periodic table, and they were going to get their dang name in the periodic table. That's just a little bit more information about, why this matters, because it explains that chemistry that we've already talked about and that we're going to continue to talk about in the future. So let's talk about some of those behaviors that the quantum mechanical model explains. So we talked a little bit, so it does help explain that trend in ion formation, right? So if sodium is that number 1 on the periodic table, in the first column, in those alkali earth metals, they all have one valence electron. So if they give up their one valence electron, then they're able to have that positive 1 charge. So they're just giving up their one valence electron, saying, hey, I'm going to stick with my core electrons. I don't need that valence electron. That's why that first column forms a +1. And the second column is the same. So the S, I'm pointing at a periodic table, you can't see, I'm doing it in my mind. So the thing is that second column, those alkaline earth metals, form a +2 charge because they have 2 valence electrons. They give up their 2 valence electrons, form that +2 ion, and so on and so forth. That's why, for example, the halogens tend to take on that -1 charge, is because they want to fill up that last big orbital they have. They're like, I'll take on 1 more electron. It's not going to bother me. So they're able to take on 1 more electron, and so they form that -1 charge. There are other behaviors besides just this ion formation and family behavior that we can use when we're looking at the periodic table. And we call these periodic trends. So there are a few trends on the periodic table, but for now we're only going to talk about 3 of them, okay? 3 trends on the periodic table: atomic size, ionization energy, and metallic character. When we get to Unit 2 and we start to talk about chemical bonding, we'll talk a little bit more about electronegativity and some more trends on the periodic table there. So let's talk a little bit about atomic size. So we can use the information from the quantum mechanical model to predict the size of every atom on the periodic table in terms of relation to each other. So remember, atomic size, we're talking about the size of an individual atom. So we know that the nucleus has that positive charge, so it's pulling those electrons in, but those electrons also push each other apart with that repulsion, right? So as you move from left to right across the periodic table, you'll see that the atomic size decreases. Okay, so the atomic size decreases because there are more protons to pull those outermost electrons in tighter. So, for example, these are only the main group elements you see on your screen, okay? So, So, like, beryllium doesn't sit next to boron, right? The transition metals are in the middle there. But if I'm, like, looking here, this is the P block, right? So they all have that same outermost space, but fluorine is much smaller than boron is because it can pull those electrons in tighter because there's more positive charge pulling on those electrons. And then we also know that the atomic size increases as you move down, okay? So as you move down the periodic table, that atomic size increases because you're adding more and more orbitals, more and more shielding of electrons by those core electrons from those valence, so they're much more spread out. So if we're looking at the periodic table, fluorine is the smallest element, helium's the smallest element, fluorine's pretty close, hydrogen's the exception, of course, to this rule. And then you kind of cut down backwards towards francium. Francium is actually the biggest element on the periodic table that we're going to talk about in this class. But cesium sits right above it. So you're kind of going like a diagonal from smallest to biggest like this. So from fluorine down to cesium. Okay. So let's do some examples. I would definitely ask you, I'm not going to ask you does it increase or decrease as you go from left to right? I think those questions are kind of confusing. What I will just strictly ask you is which atom is bigger? Which atom is smaller? So which atom is bigger from these here on the list? So first one up says carbon or fluorine. Which one's bigger? Well, if I go back to my periodic table here, I can see that carbon is here, fluorine is here. Well, carbon is further to the left, so it's bigger, okay? Further to the left is bigger, further to the bottom is bigger. So if I want to compare carbon and fluorine, carbon's further to the left, it's bigger. Let's do sodium and rubidium. So sodium and rubidium, this is sodium, this is rubidium. As we're moving down the periodic table, we get bigger. So sodium is much smaller than rubidium is. Rubidium is the bigger atom because it's lower on the periodic table, okay? So again, you should be able to start to compare them and see which one's bigger, which one's smaller by far. I'm going to leave you with the other two for you to complete on your own because you should get some practice by yourself. But remember, I always leave you with the answers there. So if you have any questions, you can try to quiz yourself and the screen or the slides have that answer for you. So the next thing we're going to talk about in terms of atomic trend is ionization energy, okay? So ionization energy is the energy required to remove an electron from an atom, okay? technically every single atom or every single electron on an atom has a different ionization energy, but we're just talking about basically removing that like outermost valence electron. So how much energy does it take to remove just those valence electrons? Remove one electron from a neutral atom. So this actually influences how easy it is for certain elements to participate in certain kinds of energy because, for example, like lithium is going to want to form a positive ion, and something else might want to form a negative ion, so those guys might want to hang out together. Preview for molecular and ionic compounds. So, again, it's going to influence that kind of chemistry because it'll be maybe how easy it is for it to form an ion, that kind of a thing. So, as you move from left to right across the periodic table, ionization energy increases, okay? So the nucleus has more pull on those electrons. They've got more protons, therefore a tighter pull, therefore a higher ionization energy. As you move from top to bottom, ionization energy decreases because those core electrons are shielding those outermost valence electrons, so it's so easy to remove them because they're barely feeling the pull of that nucleus. And so this kind of makes sense, okay? I know you're like, oh my gosh, how am I to keep this straight from atomic size? What the heck, Professor Thomas? Well, it correlates with atomic size. The smaller the atom, the stronger the pull the nucleus has on those electrons, the harder it is to remove them. So a smaller atom has a higher ionization energy because it's harder to make it an ion. Okay? So let's do some practice again, right? Let's do some practice. So again, I'm not going to ask you, does ionization energy increase as we go from left to right or decrease as we go from left to right? I'm going to ask you something like, which atom has the highest ionization energy? So let's do that. We're going to look at calcium and we're going to look at radium. So let's check out the periodic table here. We have calcium and we have radium. Well, again, it has to do with the size, with that pull of those that nucleus on those electrons. So calcium is higher up on the periodic table than radium is. So calcium is higher up than radium. So calcium has a higher ionization energy. So calcium's higher up on the periodic table, higher ionization energy. Okay, let's go check out iodine and tin. So iodine's right here, tin's right here. We're comparing left to right. Well, tin is further to the left, so it's going to have a smaller ionization energy. Iodine is further to the right, so it's going to have a higher ionization energy because it's a little bit smaller of an atom than tin is. So iodine is the higher ionization energy because it's further right on the periodic table. Okay? So again, I'm going to leave you with vanadium and francium, sulfur and strontium so that you can check that out and make sure that you can quiz yourself and understand that, okay? So we have atomic size, which means we have atomic size, so we're talking about the size of the atom. Fluorine, you kind of shoot for him as your smallest atom, and francium, you'll shoot for that as your biggest atom because francium has lots and lots and lots and lots and lots of electrons. So again, it's that core is shielding the nucleus from being able to really pull those valence electrons in as tightly as fluorine can because fluorine doesn't have a ton of electrons and it's got a lot of positive charge in those protons, okay? So we have that. We have ionization energy. How hard is it to pull an electron? Again, it correlates with that size. The smaller the atom, the more tightly those electrons are being held on to by the nucleus. And so that's a higher ionization energy. The larger the atom, the more core electrons there are for that shielding, the more the valence electrons do not feel that core or feel that pull from the nucleus. So that is going to be a lesser ionization energy in comparison, okay? Okay, so let's talk about metallic character. So metallic character is the likelihood an atom is to lose electrons in a chemical reaction. So how likely it is to give up those electrons and form that positive cation. It's of course going to correlate where we know the metals lie on the periodic table and the nonmetals. So the quantum mechanical model even explains why we call certain things metals, certain things nonmetals, and certain things metalloids. The the metals are over here, the nonmetals are over there. Trend follows just the same, right? So as you move from left to right across the periodic table, it acts less like a metal, less metallic character. So that nucleus is holding more tightly onto the electrons. And nonmetals are more likely to just fill their orbitals than to give up like a ton of electrons. So, fluorine would rather take on an electron and sodium would rather give it up, for example. So sodium acts more like a metal than fluorine does. And then as you move from top to bottom, metallic character increases. So the more electrons you add on, again, the more those core electrons are there, shielding those outermost valence electrons from the pull of the nucleus. So if they're being shielded, it's so much easier to just remove and get rid of electrons. It doesn't even notice when you pluck one. You know what I mean? Again, metallic character is going to correlate with atomic size, correlate with ionization energy. Ionization energy and metallic character, they're very closely related, right? Because ionization energy is about how hard it is to remove an electron, and metallic characters about how easy it is for an electron to give up. They're kind of just opposite concepts, okay? So the smaller the atom, the harder it is to remove an electron, the less likely it is to exhibit some metallic character. All right, here we are. Example time. Again, we're just going to compare which atom has more metallic character. So you just got to know the trend so that you can compare which one has the most metallic character. All right, so we're going to look at beryllium and carbon first. Let's go back to our periodic table, and we're going to examine beryllium and carbon. So beryllium is number 4 right here. Carbon is number 6 over here behind my big old melon, number 6 and number 4. So if I want to know which one has more metallic character, first and foremost, it should ring bells that beryllium is a metal and carbon is a nonmetal. But that aside, beryllium is further to the left on the periodic table. The further left you go, the more metallic character. So beryllium is going to be the one with the more metallic character. It's further to the left. We can compare fluorine and iodine as well. So fluorine's up here, iodine's down here. I want to compare the metallic character of those two. Because iodine is lower down on the periodic table, it's going to have more metallic character technically. So iodine's lower on the periodic table, exhibits a little bit more metallic character. All right, so again, I'm going to leave you with those last two there so that you can do them on your own. Please do it. Please quiz yourself. The answers are in the slides. So that being said, this is the end of chapter 9. So we talked about the true nature of electrons, how they're both a particle and a wave. We talked about orbitals. We talked about the Bohr model of the atom. We talked about the quantum mechanical model of the atom. We tried to compare a little bit about how they were different from each other. And then we also had, once we were able to look into the quantum mechanical model a little bit more, we were able to understand orbitals, that they are probability maps where the electrons can potentially lie in. And then when we examine the electrons in orbitals using an orbital diagram or an electron configuration, we can use that information about the orbitals, their energy, their principal quantum number, their subshell letter. We can use all of that information to determine if something is a core electron, something is a valence electron, so whether it's on the inside the core of the atom, or if it's floating around on the outside and we consider it to be a valence electron. And once we know that, we can use that information to predict how elements form ions, how the atomic size, or how big something is, the atomic size. We can determine what has a higher ionization energy, so how easy it is to remove those electrons. And we can also talk about the metallic character, how likely an atom is to give up those electrons. So there's a lot of really important information here in Chapter 9. So please let me know if you got any questions.